And hi, welcome back. Before I continue, I just want to say I think there was a mistake in the last video. I forgot to cancel off the density here. It should have been absorbed into this non-dimensional pressure. Okay, so this is what it should look like. Okay, there should be no density over here, just L over delta P. All right. Yeah, we're almost done. Yeah, we'll do that. Yeah, so that was the error I wanted to bring up, but let's just carry on from here. So we have these equations here, which we can now kind of get to include the Reynolds number. Okay, so that's how we're going to include the Reynolds number. And that's pretty much our last step. Okay, REL. Okay, Reynolds number L. This is actually REL. Okay. Okay, so that sort of non-dimensionalizes our Y equation. Okay, so review Navier Stokes non-dimensionalized. Okay, so this is the Y momentum equation, and this is the X momentum equation, and then of course we have our continuity equation, which is very simple. It's just this one. Okay, so see X momentum equation, which is over here. That's the Reynolds number, and this is the Y momentum equation. Of course, you can see there's a little bit of difference here. There's this delta P squared over L squared over delta P squared, and we need to sort of know how to deal with it. Okay, how do we the question now is, how do we actually decide if some terms are kind of negligible? Okay, so let's begin a new section. How to drop terms. Okay, so this is the section I want. How do we start dropping the terms? So I'll just copy and paste. Okay, and before that I'll just continuity. Let's call this section. I want to put a new section here, which is order of non-dimensionalization. Alright, it's non-dimensionalization. So we did all this non-dimensionalization. Okay, so how do we start dropping terms? So these are our equations over here, and we know Reynolds number is going to be some value, but we don't know how big this is going to be. Of course, if Reynolds number is very, very big, then these terms here can be cancelled. Okay, if the Freud number is very big, again this gravity term can be cancelled, sort of neglected. And again, a Reynolds number, if it's very big, this can be cancelled. But then you have this L squared over delta P squared. So there is some for when we want to determine which terms we cancel, which terms to cancel, we need to know how REL compares with this L squared delta P squared. Okay, L squared over delta P squared. Alright, so how do we do that? Okay, let's make an assumption here, very logical assumption. Okay, to start with this assumption, let's and to try and connect it to a concept, let's take a look at our boundary layer equation again, or boundary layer again, Yeah. Let's see. Yeah, I'll take out this part and take out this part and take out this. Okay. So over here we have again a flow going to the right. Alright, a flow going to the right pretty quickly, and you can say that the u infinity L over nu, the inertia terms here, inertia, it's kind of bigger than the viscosity. Alright, initial terms are bigger than viscosity. Alright, so that's the idea. Okay, and this deals with the x velocity u. Okay, so we know that inertial terms are bigger than viscosity generally for this free stream velocity, but that's not very helpful, right? Okay, so how does this compare in the boundary layer? We also don't know. Yeah, so this is kind of a question mark. However, the other thing that's we can take a look at this from another perspective, using something that's a little easier to find, and that is the v velocity, the y component of velocity. And we know that this y component of velocity is very small. This v is very small compared to this u. Okay, in fact, v over u infinity can be kind of how do you say? It can be done using this kind of a scaling methodology. Okay, v over u infinity is sort of related. The characteristic velocity, vc, I'll just call it v characteristic velocity. It is comparative. It's compared using the length scale. Okay, just now we not just now, a few videos back we came up with that. Okay, okay, so since this thing is very small, okay, we can actually sort of think of it this way, right? These inertial forces are small. These inertial forces are small, and you can even say they are comparable. The inertial forces, these are actually comparable with the viscosity, viscous forces. Alright, in other words, we can say that this v velocity, the y component of velocity, is so slow that you have creeping flow. You have a creeping flow upwards. Okay, creeping flow in y, oops, that's too much of a y there, y direction. Alright, creeping flow in the y direction. Okay, because this v velocity is so slow. Okay, so let me write that again. I'm gonna clear the, okay, the v velocity is slow. Okay, maybe I'll just write, because that looks like a new, v is slow, and then we can have sort of creeping flow in y direction. Creeping flow in y direction. Okay, I think hopefully that's pretty clear. Okay, so creeping flow in y direction, we can say that the Reynolds number is equals to 1. Problem is, which Reynolds number are we talking about? Is it REL? Okay, no, it's not REL. This is a Reynolds number based on this y direction velocity. So we can sort of come up with a different Reynolds number. We call this RE delta. Okay, RE delta, we'll define it like this, because if we have a boundary layer as such, we have u infinity here, and of course v going upwards. Okay, so this Reynolds number is based on the y length scale, not the x length scale. X length scale is here, but the y length scale is velocity, so we'll use delta as the length scale, v will be the velocity scale, and nu will be the kinematic viscosity. Okay, and this should be on the order of magnitude of 1. So let's write this down. Okay, creeping flow in y direction is our assumption, so that RE delta equals to V delta over nu. Alright, and this will be on the order of magnitude of 1. Okay, so hopefully this is a logical assumption we can make, and from this assumption we can actually come up with some relative order of magnitude. Okay, so what is V? We previously described. Okay, this V is a characteristic velocity. Characteristic velocity in the y direction. So what's the characteristic velocity in the y direction? It's actually u infinity times delta p over L. And I'll use delta p just to avoid confusion. Okay, delta p over L will be the figure of merit or whatever it is. Alright, so this is how we can substitute things in. So let's substitute this expression in here, and we want to see how this RE delta actually compares to REL. So that's why we are doing this. So how does RE, the Reynolds number in the y direction, compare to the Reynolds number in the x direction? So that's how we can think of it. Okay, and that okay, so we just do some substitution first. Okay, so first thing first, we have u infinity and nu. That's halfway through, and we have a delta p over here, so sort of have delta p squared. And we know REL is actually equals to u infinity times nu over L. Okay, so let's do this. Let's try to factorize out. Let's divide this equation. Factorize out 1 over L so that we can find REL. Okay, so what I'm doing is simply getting this part out, getting all the delta p terms out, and I am just doing this. I'm just rearranging the equation. Nothing too much there. Okay, so I'm getting this delta p and delta p out, this L out. Of course, I'll multiply the top and bottom by L so that we can see that this actually becomes nothing but REL, which is the x direction. What do you call that? Reynolds number, REL. Okay, so now this is actually very useful, right? Because now we see that REL and delta p over L squared, when you multiply these things together, they are on the order of magnitude of 1. So so this stuff sort of cancel out. All right, so let's deal with the x direction first. Momentum equation. All right, and let's use this new insight that we have gained from our assumption, where we have creeping flow in the y direction. Okay, we can use this assumption to do something. Okay, so we see that there's REL over here, and then there's this L squared over delta p squared, and this exactly is order of magnitude 1, which is very convenient for us. Okay, so let's do that. We will bring this REL in, and yes, and yes, we'll just multiply both of these in. Okay, we'll multiply both of these in, and now this thing over here is actually RE, I mean this is the 1 over the order of magnitude of 1. Okay, mathcal 01. Okay, so now you can see the usefulness of having all these non-dimensional terms scaled to the order of magnitude of 1. So all of these are on order of magnitude of 1. This one's also on order of magnitude of 1, and all that we need to compare is this REL term. Okay, this one we don't is on the order of magnitude of 1, and this one is on the order of magnitude of 1, GX star. The Freud number is big, and REL, how big is it? Okay, so let's how big is REL? So based on this creeping flow assumption, we can see that REL equals to okay, the order of magnitude of L squared, okay, delta over delta P squared. So this REL is actually, okay, I'm adding another line. REL is actually L squared over delta P squared, that kind of order of magnitude. And this is pretty big. Okay, so REL is pretty big. Alright, so this since REL is big, we can kind of sort of just neglect this term. And Freud number is big. Okay, we also assume Freud number is big, right? Which means that the inertial forces are much bigger than the gravity forces. Okay, Freud number is big. It won't, yeah, Freud number should be big. Alright, so let's just assume that the Freud number is big, so that the gravity terms can disappear, and the Reynolds number terms here will also disappear. So that's how we can use this scaling to systematically conclude which terms can be taken out. Okay, so next subsection y direction momentum equation. Okay, so actually this order of magnitude 1, I can just take it out. Maybe not. Yeah, I'll just leave it down there, just for reference. So this REL term disappears, the Freud number term disappears. Okay. Now next thing is this. Let's deal with the y side momentum. And immediately we will be able to see one of the terms disappear again. Okay, this term here will disappear for similar reason. Okay, 1 over REL, and yeah, so basically I'm just bringing this term in, and this will reduce to some order of magnitude of 1. It will reduce to some order of magnitude of 1, which is again very convenient for us. However, we are not really finished. Why? Because there is another term here, L squared over delta P squared. Right, this L squared over delta P squared. So what are we supposed to do? The next step will be then to divide everything out by REL. Okay, we want to divide everything out by REL. So the first 3 terms will be divided out by 1 over REL. this one will be divided up by REL squared. And over here on the right, we also should divide it out by REL. So let's see whether I did the equations right. Okay, so these three should be divided by REL. This will be REL squared, and this will be R1 over REL. And we basically have this over here. Okay. I hope you can see all of these terms will start to disappear because REL is pretty big. This one will again, when we bring this in, will be combined to an order of magnitude of 1. Okay, so it will be combined to the order of magnitude of 1. Okay, and this term here, it depends on, wow, that is really big. Okay, that's just way too much. Okay, kind of ran off the page there. Alright, let's do it like so. You'll actually find out a lot of these terms just disappear. Alright, very good. Okay, so you see, REL is over here, REL is over here, and okay, cancelling out. Okay, so this this term will just be order of magnitude of 1. Let's count O1. And well, the other term here, this REL over here, how can we then deal with this? We can actually get this trick done. Okay, so I have a L squared over delta P squared, and then we'll just multiply it out again. Delta P by L. Alright. So now we see this this thing over here. This will be order of magnitude 1. Okay, so I will just put simplifying, and the next thing to do is just to get rid of this. Okay, math cal O1. Okay, so this is what we can do. Alright, so now it's very easy to compare. Okay, we can of course factorize out this order of magnitude of 1 here. And basically we see something. Okay. Okay, this part, okay, for significantly, well, REL is pretty big, right? REL is pretty big. So for large REL, the whole left hand side just becomes 0. Okay. Okay. Then what you have left are these two terms. Of course, we can actually get rid of this order of magnitude of 1 if you want, because you just divide throughout by 1, it will not really do much. Okay, so this basically says that the delta P delta Y will just be a function of, you know, gravity. Of course, you compare it with the Freud number and all. So this term here is small, but it's not 0, so you can't just cancel it out like that, right? Can't just cancel it out like that. Okay, so we don't cancel out the terms. Okay, we cancel out these terms on the left hand side because they are small in comparison to the terms on the right hand side. But since delta p delta y you don't know what it is, and the only term it's compared to is this thing over here, the gravity term, you cannot just cancel it out. Alright, so we do not, generally speaking, we don't cancel out terms unless they are small with respect to some other term. Okay, so we cancel out terms on the left hand side because they're small compared to the terms on the right hand side. But these two terms, this term here is not being compared with anything. In fact, it's being compared with 0. Even a very small number, even if you have a very large Freud number, so to speak, even if your boundary layer is so thin as compared to L, it is still non-zero, so you cannot just cancel it out like that. Alright, so what we have for the y equations are that the gy is equals to this. Okay, then only if gravity equals to 0, only if your gravity equals to 0, then you can say, alright, my pressure gradient on this y-axis is kind of 0. Okay, so there you have it. Alright, so similar for the x momentum equations, or it all depends on the Freud number. Okay, so that's the thing with this, and the Freud number is very important. Okay, if gravity is 0, of course this whole thing can just be neglected. Alright, so if the Freud number is big, this term is small in comparison to these terms over here, so we cancel it out. Okay. Okay, so now after everything, now we have our boundary layer equations. Alright, so what did we cancel? Okay, we have a del p del y equals to 0, which is not very interesting there. But in general, we assume that the gravity forces are negligible. And what about our x momentum equations? Okay, x momentum equations. Of course, I will re-dimensionalize them. Okay. I will kind of skip the steps of re-dimensionalizing everything, but yeah, this is what we will get. Okay, so this is the non-dimensionalized equations, which we will just get this. Okay, re-dimensionalize. So I just call it re-dimensionalization. And then we'll just remove all the stars there, because more or less the equations are the same. Of course, we get rid of the order of magnitude of 1, because that's not really important anymore. This whole analysis is just for us to systematically see which terms we can cancel and which terms we should leave. Alright, so let me more or less finish. Okay. Oh shucks, that's the U is not getting powered to anything. Let's try again. So this becomes our equation. Of course, there's a continuity equation there with partial u partial x plus partial v partial y equals to 0, and these become your boundary layer. Boundary layer equations, the laminar boundary layer. I should make it very clear, laminar boundary layer. Why? Because turbulent boundary layers will not use this set of equations. They'll be a bit different. Okay, beautiful. Okay, so now the question is, how do we solve it? But that I will probably start in the next video. So thanks for watching. I'll see you guys again. Bye bye.